Okay, let's discuss isotopes. Isotopes are basically forms of the same element which have the same number of protons, and they basically differ from each other in the number of neutrons. And hence you can perhaps envision that if you consider, let's say, C12 isotope, carbon has 6 protons, and you consider C14, the other isotope for carbon is a C13, notice that all of them do contain the same number of protons, which is this lower number, also called as atomic number. However, comparing the mass number and number of protons, you can say that the number of neutrons in case of C12 is 12 minus 6, which is 6. In case of C14, n is going to be equal to 8. In case of C13, n is equal to 7. So different isotopes of the same element are going to be referred to as isotopes. Their properties might be a little bit different based on their stability. And so, for instance, C14 is a radioactive. It's the radioactive isotope of C12. Which has a half-life of about 5,800, almost 5,800 years. And so what that means is that every 5,800 years, the amount of C14 content that is present in that sample is going to become half of what it was originally. And so one can figure out the number of half-lives and hence be able to determine the age of a material, something called as radioactive isotope dating. If you've seen Jurassic Park, the movie Jurassic Park, essentially recall that mosquito that had fed on the dinosaur's blood. Essentially, that blood was used to figure out the age of in which those dinosaurs lived. So it's a pretty interesting technique, something we'll discuss in general chemistry too in a little bit more detail. But realize for now, isotopes will have different mass numbers and hence they will have different number of neutrons as well. Now, based on the abundance of each isotope of an element, you can perhaps envision that the atomic mass that you see on the periodic table is going to be dependent on these natural abundance. So what you see, the number that you see, for instance, in case of oxygen or nitrogen, whichever you're referring to, that number comes not only on the basis of the most abundant element, but you also take into account the rest of the isotopic units. So, for instance, if you wanted to figure out the atomic mass, which really is some people actually refer to it, they call it atomic weight. So I should probably just clarify that right now. The word weight is kind of like a misnomer because the word weight, according to physics, should be referred only to a force. But atomic weight, or one can refer to it as a relative atomic mass. So we should refer to it as the atomic mass. But that is essentially a weighted average keeping into account all of the isotopic unit. So like I was trying to discuss with you, for the case of carbon, you have three isotopic units, and so what you'll do is you will look at the abundance of each of the three isotopes of carbon, and you will take a look at the mass of each of the isotopes, and when you put them together, that's how you get your atomic mass. So you can say that atomic mass A is going to be equal to mass of the first isotope times its abundance plus mass of the second isotope times its abundance plus mass of the third isotope times its abundance, and so on and so forth. Tomorrow, if you have another element, let's say lithium, and it has 7 kinds of lithium, like 7 kinds of isotopes, then you have to include the masses of each one of those. Now, you can perhaps realize that since this is a weighted average, the most abundant element is going to be the one that's going to play the most significant role in terms of the total mass. For instance, if you consider chlorine, chlorine has two isotopes at 35 and 37, just ballpark. The one that's at 35, that's close to about 75%. These are only, rough numbers, not exact. The one that has a mass close to 37 is about 25%. And if you look at the atomic mass, that's like 35.453. So it's closer to the one that is more abundant as compared to the one that is less abundant. I think there is one question that we are going to solve for you. So let's talk about the third term that you can see on this slide, which is the average isotope mass, sometimes also referred to as the relative isotopic mass. Two things. If I just say isotopic mass, that would just basically mean the mass of a certain isotope. For example, for C12, it will be 12 point whatever. For C13, it will be 13 point, so on and so forth. So the mass of a specific isotope is referred to as an isotopic mass. On the other hand, if you're thinking about the relative isotopic mass or average isotopic mass, numerically it means exactly the same as an atomic mass, and the way you calculate is also the same. The only difference between the two is that the average isotopic mass does not have any units. So you will not use the AMU units for that case, because in order to get there, essentially you have it relative to, or averaged out, and then have it relative to the C12 isotope of carbon. And since a Dalton, or 1 unit, is normalized against carbon 12 as your standard, as your relative standard, essentially using the dimensional analysis method, you would see that there is the mass, whatever mass you have, that's essentially normalized against C12 as your relative standard. So that's how the units are going to cancel out, and it'll be a unitless quantity. But what it means numerically is exactly the same as an atomic mass, and the way you would calculate would be based on the abundance of the isotopes put together. All right. So let's see if we are able to apply information that we have heard so far upon some of these questions. The question is, what are the atomic numbers for the following? So what do we need for that? Yes, you're right. You need a periodic table, and you need to look for copper. The periodic table is not going to give you the name. Once in a while, you might, but that's not a standard periodic table. The element should be looked for using the symbol. So copper comes from cuprum. So Cu is what I'm seeking. If you look at the periodic table, you will see the number 29. So the atomic number Z is going to be 29 for the case of copper. For sodium, it's natrium, so it's Na. Z is going to be 11. Sulfur, S. Z is going to be 16. Oxygen, O. Z is going to be 8. Hopefully you got that right. Let's go forward. The question is, what are the atomic masses for the following elements? So is that something that you can get straight from the periodic table? Yes, you can. So atomic masses, do appear on each of those unit tablets for each of the elements, and that is that fractional number that you see for each of the elements. And so for iron, you're looking the fraction right under Fe. So it really depends on the periodic table that you're using, but on the one that I have in front of me right now, this is 55.45 AMU. Magnesium is 24.30 AMU. Bromine is 79.9 AMU, and xenon is 131.59 AMU. But as long as you know where to look for it, so again, recall, you have that little tablet for each element. There is some element X. There is a, um, there is a full number, which is the atomic number, which is essentially on top, and you have your atomic mass as a fractional number, typically at the bottom. All right. What are the mass numbers for the following? Would you be able to calculate the mass numbers for the elements from the periodic table? The answer to that is no. Mass numbers are nothing but number of protons and um, neutrons put together. Um, in a question like that, you would need, like I said, you would need the number of neutrons and protons both in order to figure that for a specific isotope. But when they have not specified that, you can simply take that to be the uh, the roundup version of your atomic mass, because that would mean that they're referring to the most stable isotope, and you'll go from there. So for instance, if you consider nitrogen, nitrogen is at 14.001. I'm going to round down to 14, and so nitrogen 7 and 14, that would mean that the mass number is going to be 14 for that. You can work out the rest of it. Okay. The question is, the isotope selenium-75 is used medically for the diagnosis of pancreatic disorders. How many protons, neutrons, and electrons does an atom of selenium-75 have? So that's pretty straightforward. Realize first things first. The lower number, that's same as the number of protons, and that's atomic number. So I'm going to say 34 is the number of protons. Now notice there is no charge on the right hand side. Typically the charge is what appears on the right hand corner, and there is no charge there. That means that it is a neutral species. And so that would mean that essentially you have 0 for the charge, and the number of protons is going to be equal to the number of electrons, because it's a neutral atom. So that's 34 as well. And now if you have to determine the number of neutrons, that's pretty straightforward. You basically look at the mass number. From the mass number, you're going to subtract out the number of protons, and so that's going to give you a 41, and that would be the number of neutrons present in that species. Okay. An atom of element X contains 47 protons and 62 neutrons. Identify the element and write the symbol for the isotope in the standard format. This is pretty straightforward. When you look at 47 protons, you should be thinking this is the number of protons, and hence it's also the atomic number. That means my Z is 47. And if that is 47, and the number of neutrons are given, that means lower number is 47. You are reading on the periodic table and you hit silver, Ag. And since upon adding 47 and 62, you're going to get 109. This is the standard format. You're talking about Ag 109 or Ag 107 for the mass number, 47 for the atomic number. Okay. Let's take a look at another one. Chlorine has two naturally occurring isotopes, Cl35 with abundance of 75.77% and 34.969 for Cl37. The abundance is given. The isotopic mass of that is 36.966 AMU. What is the atomic mass of chlorine? So we are asking A, when two isotopic moieties are given, M1 is 34.969. A1, the abundance of that is 0.7577. M2 is 36 This is multiply. 36.966. I'm going to multiply that times 0.2423. And now you work out the math. Make sure that you keep the sig figs intact, and in that, whenever you are multiplying two numbers, you look for the least significant figure. Whenever you're adding, you're going to look for the most decimal place, and when you work this problem out, your answer comes out to be 35.45 AMU. Okay, let's take a look at another one. I've been given phosphorus. I'm supposed to basically fill up this grid. So phosphorus is given, no charge is given. That means it's a neutral atom. Phosphorus on my periodic table is at 15 for the value of Z. That means that's the number of protons. That means the number of electrons is going to be 15 as well. And since it's 30.99, so that's 31. 31 minus 15 is 16. So that's the first one. Na plus, Na has a Z of 11. Since there is one positive charge, 11 minus 1 is going to give me only 10 electrons. So since there's only 10 electrons for the 11 protons at the center, you have that one positive charge. It's a 23 Na. This is how it looks. So 23 minus 11 will give you 12 neutrons. If you do the same thing for S2 negative, you have 16 and 32. So 16 protons, 16 plus 2 electrons, because that's why you will have that negative charge, and that will give you 18 electrons. And 32 minus 16 is going to give you 16 neutrons. So that's how you're going to figure out the protons, electrons, and neutrons. Let's see. Okay, let's talk about nomenclature of compounds now. So we'll talk about bonding first. What are the two kinds of bonding that are possible? And then I'll talk about nomenclature. So there are two kinds of bonding that are present in compounds in general. One is covalent bond. The other is ionic bond. And if somebody asks you, well, why does bonding occur in the first place? If you think about chlorine or if you think about sodium, why do they need to bond? And the answer to that is you should be thinking along those lines, something you have heard in the past, and that is stability. You want your atoms of all elements to be as stable as possible. So on one hand, sodium will lose one electron and achieve stability. On the other hand, Cl will gain one electron and achieve the stability. So stability and achieving that octet is the primary reason that you're going to see bonding. And it can be achieved in two ways. The first method is the ionic method. The second method is the covalent method. And it really depends on the compound. What are the elements that are present in the compound, which is what is going to decide whether the bond is going to be an ionic bond or a covalent bond. So for instance, if you have a non-metal bond, it's going to be a covalent bond, because the only way that the two atoms can come together is through sharing. So for example, if you consider oxygen and hydrogen. Oxygen has 6 electrons of its own, and if it somehow gets 2 electrons more, which it can if hydrogen is willing to give its electrons, now oxygen is going to start having 8 electrons, so that will be pretty happy. Hydrogen, on the other hand, has only 1 electron. So if it is able to share an electron, so if it gets electrons from oxygen and the other hydrogen also gets electrons from oxygen, essentially they would get a filled duet. And so by sharing their electrons in forming that bond, oxygen has achieved its octet, both the hydrogens have achieved their duet, and they have the correct number of electrons, so they have achieved stability. And so the way you can perhaps think about this in your daily life is, if you wanted to start like a joint venture capital, and you had 10 grand, I had 10 grand, together we are going to start something worth 20 grand, and each of us is going to have an equal say in that. So we will have 50% of that joint venture together. The ionic is a little bit different, and I'll talk about that in a little bit. But before we talk about, let's talk about how we would be able to name these compounds. If you have a covalent compound, which by the way sometimes is also referred to as a molecular compound, and notice the word binary. I'm saying that these are binary molecular compound. That means all you have in that formula is two nonmetals, and because it's supposed to be a nonmetal type of a bond, and there should be only two nonmetals. So something like water, for example, H2O or NH3, these are binary molecular compounds. Your first step is to identify which one is the more cation like element and which one is the more anion like element. Now typically on the periodic table, perhaps envision that more an element is on the left side of the periodic table, especially towards the bottom, it is going to be more cation like, because that's where most metallic character metals are. Likewise, more anion-like character or a tendency to gain electrons is going to be seen when the size is small, and it's more on the right-hand side of the periodic table, more right around where fluorine and oxygen are. So those are the best nonmetals. So nonmetals always want to gain electrons, metals want to lose electrons, and once you have identified that, essentially you would be ready to name the compound. So all you have to do is, at that point of time, you have to retain the name of the cation-like element. So let's say your molecule was HCl. Hydrogen is right over here, so it's more on the left side. Chlorine is, so the first one is fluorine, the second one will be chlorine, somewhere here. So chlorine is on the right side, it's more anion like. Hydrogen is cation like. I'm going to retain the name of hydrogen. Chlorine, I'm going to drop the INE, replace it with IDE, the name becomes hydrogen chloride. Notice I have only one chlorine here, only one hydrogen here. Typically, in order to talk about the number of such atoms, I would have to use the mono, di, tri, tetra, the Greek prefixes. But in this case, hydrogen and chlorine can only come together in this specific format, which is why we have dropped the mono. We are not calling it monohydrogen monochloride, we just call it hydrogen chloride. On the other hand, if you had something between nitrogen and oxygen, nitrogen is on the left side, so you retain its name, you say it is nitrogen, and oxygen is going to basically drop the -egen part and write down, replace it with IDE, and so the name becomes nitrogen, not just nitrogen oxide, but nitrogen monoxide, would be more appropriate. Likewise, if you have NO2, you would call it nitrogen dioxide. If you do not use the mono and only use oxide, that will be half done. And it can cause some confusions, because some people would refer to a nitrogen oxide as, just a generic term, nitrogen oxide. And so if you have a situation like, let's say, N2O, then you have to start specifying the number of nitrogen atoms here. So that becomes dinitrogen monoxide, or nitrous oxide is the common name. Nitrous oxide. Likewise, if you had an N2O4, you would call it dinitrogen tetroxide. So you specify the number of atoms using the Greek prefixes. You retain the name of the cation like element, nonmetal, and you replace the suffix essentially is IDE. So you replace the last couple alphabets, you drop those like INE for chlorine or fluorine, and IGEN for oxygen, UR for sulfur, ROUS for phosphorus, and basically replace it with an IDE. All right, so let's see if we can apply this information further. So this slide basically gives you all the Greek prefixes up until nona for 9. So mono, di, tri, tetra, penta, hexa, hepta, octa, or nona. Deca if you had 10. So for instance, CO, carbon monoxide, CO2, carbon dioxide, and that's able to distinguish the number of oxygen atoms. SF4, that's sulfur tetrafluoride, because sulfur is more on the left side of the periodic table. So NCl3, between nitrogen and chlorine, nitrogen is on the left side, so that will get to retain its name, nitrogen trichloride. So you do have to specify the number of chlorine atoms, and the word tri, the prefix tri, does that. P4O6, 4 means tetra, so tetra phosphorus hexa, O6, hexoxide, disulfur difluoride. Disulfur because there's two sulfurs. Fluorine will drop the INE, replace it with IDE, and there's two of those. That's why the word di. So disulfur dichloride should be S2Cl2. Iodine monochloride. Iodine is I, chloride is Cl, and it says mono, so we'll keep it as is. Nitrogen trioxide. Nitrogen is N. Oxide means oxygen, so that's O. There is 3 of those because it's tri. We call it NO3.